Next up, the last talk of the session is Dr. Lauren Ferguson. She is the Digital Transformation Lead in the Materials and Manufacturing Directorate of the Air Force Research Laboratory in Dayton, Ohio. She earned her PhD in mathematics from Texas A&M University, where she became interested in mathematical applications to material science problems through an NSF fellowship. She spent 8 years developing state-of-the-art simulation tools for composite materials that accurately model post-processing material state, capture complex damage patterns due to service loads and environments, and predict remaining life. For the last 2 years, she's pivoted to driving digital transformation efforts at AFRL, including facilitating pilot programs to seamlessly integrate labs for streamlined data collection and analysis, and to make Google Workspace and Cloud tools available to foster collaboration with global partners. So, Lauren?
Great, thank you very much. So I'm really excited to talk to you about some of the things that we've been doing in AFRL to integrate our labs. So actually a number of the things I'm talking about I'm already hearing across some of the different talks today, which really involve a lot of culture change that we need to affect. So to get started, I wanted to acknowledge my colleagues who have been building the tools that I'll be discussing. So Matt Jacobson, Jason Teese, Grant Phillips, and Jed Helmers are all from our Hangar 18 software factory, and then Tom Bainline and Tyler Steggy from our Material State Awareness branch. So in this talk, I'm going to go over the current challenges to integrating our labs at AFRL and our vision for fully integrated labs in the future. Then I'm going to talk about our recently developed solutions toward this vision with some notes on what the next step should be. So one of the challenges to conducting research at AFRL is that many of our equipment controllers cannot be directly connected to our internal networks. These controllers tend to run older and/or specialized operating systems and typically require some level of administrative privileges for proper functioning. Admin privileges are also required when the controller and corresponding equipment undergo calibration or other servicing. Many of the settings that standard networked government systems require cannot be used on these systems, since they can tie up compute resources and could interrupt the testing on the actual equipment. That could be very dangerous if we are in the middle of a test and it gets stopped in some way that it's not expected. Since these conditions and policies prevent direct network connection, our current data collection process is often highly manual. We have lack of network connection as well as our current internal research culture sees users documenting experiments in physical notebooks, so the information they capture, in addition to the actual measurement data, is rarely digitized. So we have a lot of this, we're still using these manual notebooks to capture all of our data, and that's just in our isolated lab. So once the data has been collected in the lab, which could include additional processing like image reconstruction, then we generally need to share it with our collaborators for further analysis. And this could be internal working groups or external partners. So we want to be able to send that data out, and we really want to be able to collaborate on that data, not just send it out beyond the fence. We want to collaborate it and still have control over it. But typically, this current data process involves multiple time-consuming transfer steps via CDs or portable hard drives. First to isolated air-gapped machines, then to network systems, high-performance computing centers, and cloud storage. Due to the size of the data sets, we often resort to sending data by snail mail. And that's very slow. Obviously, these slow, manual, and paper-based data processes hamper our ability to collaborate effectively and competitively. In the Materials and Manufacturing Directorate, we would instead like to achieve seamlessly integrated labs, where data is fair, which I'm sure you guys are familiar with, findable, accessible, interoperable, and reusable. And in addition, we want to be able to do things like provenance and quality of the data. So we want to be able to capture all of that for the data that we use. And in particular, we need integrated search capabilities across all of our accessible data lakes with searchable metadata for enhanced findability through natural language processing. As we've heard all about the AI/ML tools, we've been talking about this during this conference. We want to be able to apply those to the data that we have. Provenance of the data and a measure of data quality are important for identifying authoritative sources of truth. We could also enable an Internet of Things for each lab to capture environmental conditions and inform future work with insights from machine learning algorithms. finally, we can streamline collaboration with all of our partners with secure but efficient access mechanisms. So that's kind of the goal of like having a completely integrated lab. This is what we really want to be striving for. I'm going to talk specifically about this piece, which is the seamless data ingestion with metadata. So we've developed a new approach for this lab data ingestion while capturing corresponding metadata. Our approach is specifically designed to help users ensure that data is findable for future reuse. I will be discussing two enabling tools that we have developed in-house towards this goal. The first is Norms, which assists users to easily generate metadata, and the second, which is called Spike, automates one-way data transfer from isolated systems. So talking about this first tool, which is Norms, the concept behind Norms, which stands for No Omission Research Management System, is to enable users to create digitized metadata while minimizing additional workflow overhead. Norms integrates into a workflow seamlessly by using the principles of reactive documentation. Reactive documentation helps the user to remember to document their data as they go. The user's primary focus during an experiment is on the data, so it's easy to be distracted from writing documentation. However, data still needs that documentation in order for it to be maximally useful. One option to fix this issue is just to train the users to focus on the documentation while generating data. But that puts all the burden on them, and that requires a complete culture shift in the way that people work and the way that they do their experiments. So the other option is to look at what's happening on the computer when they collect the data and react to the events that are happening in order to create opportunities for them to enter the data that's needed and have that all be done automatically. So in particular, if a file is generated during a scan, a reactive documentation system can react to that event and show a documentation window. The user no longer has to remember to document. It's part of their workflow automatically. With reactive documentation, it becomes easier to start documenting data. Creating documentation should also be as efficient as possible to allow the user to return to their primary task, which is conducting the experiment and doing the research that we all enjoy. So the next step is to help assist this. Let's get the next, there we go. So we've got two steps here with this Norms tool. So the first two tools within the Norms suite that I want to talk about first. So the first is called BASE, which is the Barcode and Specimen Station. It allows users to create and print 2D barcodes that contain important information about items of interest that need to be tracked and documented. So barcodes can be designed for any physical objects that you have in your lab that are needed for an experiment. And they can be designed for specimens and plug and play machine parts, or just any physical thing that you have in your lab. So that could be things like probes or tool heads, and they can all be done with these custom templates for your barcodes. The barcodes can contain any information that you would define prior to the actual experiment, and typically it's information that's not likely to change. So for example, probes may define the size, the power, the calibration, while specimens may describe dimensions, storage location, processing properties, etc. Barcodes provide quick, accurate, and consistent documentation for norms. This is particularly helpful in isolated labs where there is no access to a centralized database. Users can scan the barcodes while a documentation window is open and add that information to the metadata set for an experiment. So basically, you already have some of that data that's collected in a barcode. When you start the experiment, you just scan the barcode, and all of that information is automatically populated into your metadata set. Using barcodes also has other benefits. The act of barcoding items creates a process to apply consistent formal documentation to lab items, even when they come from disparate sources. BASE can also save the barcode information to local JSON files, and that saved information is then pulled into a database to answer inventory questions. And BASE itself has a search mechanism for these items, which is particularly useful if you want to find things on that local system when you're not looking at your centralized database. Templates control what information is entered into the barcode, and template creators can limit a user's possible input values where necessary to ensure that the barcodes are consistent between different users. Barcode inputs can be as restrictive as you can only select from a dropdown with the predefined list of values, or you can make it really flexible and just have a text box that the user can enter any information that they want. So the second tool that I'm going to be talking about is called EASL, which is already up on the screen, which stands for Experimentation and Simulation Electronic Logbook. EASL is the software that actually implements the reactive documentation system. So it launches at the beginning of an experiment to store data that you can scan from the barcode or any data that you want to capture at the beginning of the experiment. A template for this data may also be created for each experimental setup. So this is where you can tailor your templates to your particular lab environment for the kind of data that you anticipate capturing. It prompts the user to fill in information known at the beginning or the end of experiments. You can pop it up at the beginning or at the end, depending on the kind of triggers that you want it to act on when you're running your experiment. The added metadata that the user might add could be things like the funding project, the date of the experiment, the technician who executed the experiment, the room conditions like humidity or temperature, or any other information that you wouldn't know until you're actually conducting the experiment. There's also a space for supplemental notes. So for example, if something happened during the experiment that was unexpected, or if you tweaked a setting, you can capture all of that information. The metadata is stored in a standard JSON format and then packaged together with the data that's generated from the experiment. EASL also supports plugins that can be called after a scan is complete that can generate additional metadata or files to include with the experimental manifest. Each plugin also provides a list of metadata parameter names that it will create so that the user is not double documenting. So another source of information about the experiment comes from the interactive controller software. So the actual settings that the user is setting on the controller to do the experiment. So in order to kind of capture that information, EASL supports taking screenshots during a documentation session. The areas of the screen can be predefined as regions of interest, and each region gets a label and supports an additional comment space so the user can actually make a note on the things that they're capturing. This makes, and you can do all of that at just a touch of a button to do those screenshot captures. This makes the process of creating documented screenshots faster and easier. And once all the files and the process of creating metadata have been generated, the entire manifest is backed up to a local database in the isolated lab, which is accessible with a third tool, which is called Logbook Viewer, which I don't have a screenshot of here, but this is the tool that you can actually use to search the database or the manifests that you've already created for your different experiments. So you can go look up experiments in the past, and you can retrieve those and search for those easily. Logbook Viewer provides a high-level overview of activity occurring on the machine by showing a list of completed experiments with relevant information. It also provides tools for local storage management, for example, the ability to sort by scan size so that you can assist in making decisions on when to offload data from your local drive space when you have limited drive space there. So NORMS has been actively used since 2016, although it's still in continued development. So a lot of these things have been ongoing. And since that time, we've had over 200 specimens and 300 transducers that have been barcoded with BASE. And in that same time, 7,000 individual measurements have been documented with EASL and are locally retrievable through the Logbook Viewer. So again, the primary focus of NORMS is really to enhance that metadata collection and consistency on local machines for sharing with others. So that still leaves the question, how do I share the data outside? So once the data has been generated, it still only lives on that isolated system, that isolated network. So the second tool I'm going to be talking about today is Spike, which enables one-way data transfer from your isolated lab into databases that are available on other networks. In order to satisfy network requirements, the data has to be scanned for potential viruses. And previously, the only method to do this was to put it on a hard drive, walk over to an air-gap machine, scan it, walk it over to your computer, download it, and then it's still only on your local computer. So then to share it with others, you have an additional transfer step and potentially a mailed hard drive. So each of these steps, again, are manual and slow. And with Spike, we can automate this data transfer directly from the experimental controller to a central database repository, which is automatically shared with project partners. So again, from that cultural standpoint, we talked in some of the other talks about there's a resistance to sharing information. Part of that resistance will be helped if it's really easy to share the information. So if you already have all the data going to a place where everybody can access it, that's one less hurdle that your users have to experience. So one of the databases that we use to share this data to is called Hyperthought, which is a NoSQL web-based platform that was also built in-house. And it's from a blend of open source and commercial technologies, which is specifically designed to support scientific discovery, learning, and collaboration. Hyperthought associates the flexibly defined metadata that we're collecting from norms, as one source in particular, with the lab data to enable complex search queries, cross-referencing, experimental data pedigree, and workflow management. The impact of this solution has been significantly faster data availability, including searchability, to all project members. So a transfer and scanning process that used to take 3 hours can now take a few minutes, with one of our X-ray computed tomography labs transferring multiple terabytes of data a month. So it's really been a game changer for people in the lab that have to conduct these experiments. And even we're still working to improve the speed of the transfer. The best thing about it is you don't have to babysit the transfer. You just start the transfer and then you can go work on your other things. So in addition to transfer, the Spike tool can also be used to select a parser to extract embedded metadata from known data types. Spike can parse these data files prior to upload so that the parsed metadata is automatically associated with these files. Parsers are written in Python, and users can contribute their own parsers by extending the base parser class. The JSON parser is what's used to handle the data generated by norms, with other parsers currently in development for common files such as XML, CSV, TIFF, etc. So that's kind of a quick overview, but let me give you a quick note on where we're going next. So we're rolling out both norms and Spike to other isolated labs within our directorate, the Materials and Manufacturing Directorate, as well as extending the solution to other labs in AFRL. We are constantly working to improve the tools, and for norms in particular, we're planning improvements to the GUI for an enhanced user experience, including better templating for user input and interactive tutorials for both easel and base. And that includes both the installation and configuration. There will also be some automated hints to help the user recognize when they updated a control parameter between experiments to ensure that this parameter is accurately captured. So basically, you might be in the middle of experiment and you're testing things, and then you realize, oh, a parameter needs to be changed in my experimental controller. I go ahead and change that parameter. It'd be great if the system automatically recognized that and prompted you as the user to say, hey, do you need to capture that this parameter has changed? We also plan to release this as open source code, so that is definitely in the works. We would like to make this more available. Again, the whole goal is to make it easy for users to capture this metadata. So it's not there yet, but it's not made available yet, but that is our plan. So please reach out to me if you would like to know more. For Spike, we're looking to automate the suite of standard parsers so that standard file types can be automatically parsed using the suite while allowing users to select additional specialized parsers for selected files. So right now, one of our limitations is you can only use one parser per file. We'd love to be able to have a couple different parsers so that you can have like a generic JSON parser and maybe, or a generic XML parser or something for an XML file. But then if you know something specific about that XML file, you can add some additional information. In order to better capture usage metrics, we're also looking at some monitoring features that we'd like to incorporate that we can report on the transfer packet size, so the number of files, max file size, total packet size, and things like that, as well as the time to transfer, because we really want to be able to report out the time improvement that we're actually saving and give people an idea what to expect when they start to transfer so they know how long things will take. So looking back towards this vision of our fully integrated lab, we've identified a number of different places where we can continue this effort even beyond these tools that I've talked about today. First, we're currently working to extend Spike to enable transfer into our newly available cloud-based systems so we can do in-situ collaboration and analysis with our additional partners. So, we want to be able to do this beyond even our local network things. We want to be able to reach out and talk to any of our partners and be able to run analyses in-situ where the data lives. The other thing we're looking at is two-way communication. So this is great for transferring data one way out of the lab, but we'd like to do other things like remote lab monitoring for one thing. So we'd like to be able to know when lab conditions change. So a lot of times we might be running an experiment overnight. We'd like to know immediately if there's something that's happened in the lab. Maybe the humidity has spiked, or maybe there's a water leak or something like that. So right now, do we even get that information, first of all? And if you do get that information, you would have to physically come into the lab to shut down the equipment. So it'd be great to be able to remotely shut down that equipment. Two-way data transfer would also permit access to software packages that are currently updated manually. And so we'll be able to pull those packages down from some local location where we can have those accessible. Also, with the advances in AI/ML, as I've been hearing about, all these natural language processing tools that we have available now, we'd really like to tie these solutions into our database to enhance searching and discover new insights into our data. So it's been really cool to see the different talks over this conference to see what people are doing with that. There's a lot of growth, I think, that we have opportunities to take advantage of for our data. And then finally, we'd like to complete the loop by using these data insights to inform and even autonomously create the next steps in our experimental portfolio. So really going towards that autonomous research where a lot of these things, a lot of these decisions can be taken over by the AI and free up your researchers to do other things that they have that they can use their expertise in. So that's just a quick overview of some of the tools that we've been looking for. Really excited to see where we go in the future for these sort of completely integrated labs, and especially speeding up some of the toil that we have, which is just the difficult things of transferring data and getting access. So with that, I'm happy to take any questions.
All right, questions?
So really cool work, right? And definitely, immediately applicable to implementing the DoD's data strategy, right? I guess my question is, you must have, at least I presume, you must have had to break down a lot of bureaucratic barriers, right, along the way. Can you speak to how you did that, or are doing it?
So you're right. There are a lot of these issues are not technological issues that we're facing, they're policy issues, right? So I think one is just making the case, and I think a lot of the talks we've heard today are helping make that case that, hey, we're behind, and the only way to catch up is to be a little bit more risk tolerant. And so partly it's showing that, partly it's showing that a lot of the technology that we have now that's enabling some of these secure steps has changed over time. So a lot of the policies are based on the state of the art from 20 years ago, where you had specific reasons for, like, I don't know if you guys still have to change your password every 60 days. I know I do. And that's really from an old technology policy implementation. So, now we could do things like two-factor authentication. So we could do a lot of the technologies has advanced, the policy has not advanced. So trying to make that case, I think that's where we're pushing through and really having to prove to the people who are doing our authority that gives us the permission to implement these kinds of things, and showing them that the solutions that we're coming up with are secure. They're just different from the way that we've done things in the past.
Other questions? Oh.
So I have a question about, essentially you kind of talked about how you were kind of labeling a lot of the different lab equipment and samples with the barcode so that you could quickly, scan and collect the descriptive metadata. I was wondering, what's the extent of that, and kind of the more general question, at what point or how do you decide when you've collected enough metadata or all the metadata about the right things?
Yeah, so that's probably a more difficult question to answer, right? Because on the one hand, people want everything. On the other hand, nobody has time to write down every possible thing that they need. So I think kind of at a first pass is you want to definitely make sure that you're collecting the metadata that you're already collecting in a manual way. So the things that you can already anticipate that you're going to be asking the questions of, that's where we start. The other place, like with some of the parsers, is the metadata that's easy to collect. So especially for data formats that are open, that you can find that information and capture it, that's kind of the places that we start. But I don't know if we have a good answer for when we've collected enough. It's really about, do we even, at this point, our first focus has been to even collect the data in a place that's accessible. So that's kind of been our first target. I think as we start using these tools, of these AIML tools for more insights, and realize, hey, there's some things that we're missing, I think that will help us to answer that question. Just a side note on that topic, though. So one of the things that we've also struggled with is a lot of the tools and equipment that we have, specialized equipment, and they also come with a specialized proprietary data format that can only be read by their equipment. So that's something that I would love to avoid.
Okay, looks like we are out of time. So let's thank our speaker again.